So if we take a look at a traditional DCOM application, we have an application which is split across two machines. The client takes input from the user, say, and fires off a request to an order component. The order component is marked as transactional, so a transaction is started at that point. The order component updates an order database and then fires off a request to the shipping department, which is mapped by a shipping object. The shipping object then updates the shipping database, having done whatever it needs to do to do that shipping order, and then returns data back to the order process, which may or may not choose to put something back in the order database. All the parts of the application in this case are done under the same transaction scope. So in order for the transaction to commit, all the pieces of the application have to be available at the same time. So the order process and the shipping process and the databases all have to be available for the transaction to commit. This is good for a class of applications where this is necessary. And if we go to the travel agent example, the client wants to see an immediate response to figure out whether the request that he made is actually a valid request. So he needs to know whether that is actually a valid travel booking and that the event or whatever happens to exist. So this is an ideal case for the DCOM distributed application. It's a great programming model, DCOM. It provides a synchronous procedure call mechanism, which is just like programming local routines or method calls. All our details of remoting the call, putting messages on the wire, are all taken care of by the DCOM runtime. You pass parameters to the method calls just as you would normally, and you get returns back, or returns via parameters or via status codes back to your object. It's very simple to write and understand because it fits exactly with the model of programming that people are used to. And application calls are the same as direct calls to methods and procedures. There are some restrictions, however, on this programming model. The component lifetimes have to overlap, as we've discussed before, that both the client and the server both have to exist at the same time for the transaction to succeed. So in this particular instance, the application isn't tolerant to network glitches or server downtime or when the server's swamped by work. So if there's too much going on the server, the client may see a failure. And the whole transaction fails if any particular component's not available. For some applications, this is the only solution available where the client sees a commit, he knows that the whole transaction's complete, and he sees a real-time view of the data. And this is a good programming paradigm for those applications. Let's move on to messaging applications. There are many applications where a single business application can be split down into smaller individual transactions, and these can be separated in time. The only requirement is all the pieces of the transaction are done eventually, where eventually is defined by whatever the business model happens to be. So let's look at the same application, but this time, rather than use DCOM, use message queuing. What you can see so far is we have a client which sends a request to an order process, and the order process updates the order database and queues a message which will eventually get to the shipping object. The queuing of the message and the updating of the database are done as a single transaction. So if the order doesn't get to the database, then nothing's put in the queue, it's rolled back, and vice versa. So we still have the guarantee that if there's a message in the queue, the order is actually logged in the database. If we go on to see what happens next, is the messaging subsystem. In the case of NT, we're using MSMQ as the messaging subsystem. That's responsible for moving the message from the client to the server. And it does this using its own transactions. So it transactionally moves the message from the client to the server, and it puts guarantees on delivery and reliability. So the message is guaranteed to get to the server and only guaranteed to get there once. The message can then be taken off the queue at the server end by a shipping object. And that shipping object can update its shipping database and take the message off the queue and update the shipping database, and that's done as a single transaction again. That's done as a single transaction again. So we can guarantee that the shipping object, that the ship request will only be put into the database if the message is taken off the queue and vice versa. So in this case we have 3 independent transactions making up the original business transaction. And we've got no loss of data integrity because everything's transactional, and we decompose the work into multiple pieces. So why use messaging? Orders can be submitted without access to the remote resources, so that means that the system is highly available. The client can continue to take orders even if the server's not there. So the server might be short of resources or overloaded, the network may be down, the server may be down. In all cases, the client can continue to take orders. And end users are completely unaware of issues with the server. For many applications, it's possible to take work out of the critical path of the application. And when I say critical path, what I really mean is what's critical to ensure the success of the business. So for example, if we go back to the travel agent example, it's critical for the business, for the client to take requests or orders from customers. If a client phones up and the order system's unavailable, then the client's likely to phone somewhere else and you've lost the customer. So you really need that piece of the system to be highly available. On the other hand, it's important to the business that whenever an order is submitted, that the credit card details are checked. It's not actually necessary to do that at the time that the client phones up. The credit card company or credit database may be remote, maybe somebody else's database, almost certainly slow to access. So you want to take that out of the critical path of the business so that you can get more client requests in at any one time. And if the credit card, say, fails to be accepted, then you can always back out the booking later on, and that doesn't affect the business in any way. As a degenerate case of the server not being there, offline work is where an application is designed to work when the server's not there most of the time. And given that 40% of new computers sold are mobile, this fits nicely with the model of the hardware being sold. And once you've decided on the work that can be deferred, it's up to you when that work's actually done. So it's often a good match to the operational or business needs, and any non-critical work can be bound up into a single package. So in the case of the credit card example, we may choose to make a single connection to the credit card company and validate multiple requests at the same time. So we can batch up work in that way by controlling the scheduling. A bit more about scheduling convenience. Not all the work needs to be done in a single transaction, as we said. The client can collect together all the requests, all the input data needed for a request, and send that as a single unit to the server. The server's queue driven, so all the data that's needed for the request at the server is available to the server locally from the queue. It doesn't need to go back and ask for the client. So we can reduce the amount of network traffic. The server component only needs to be instantiated while it's processing the actual message. So it can take the message off the queue, do whatever it needs to, and then that server component or that instance of the component can go away. It doesn't need to wait for user input. Server component lifetime is one of the major factors to scalability at the server. The shorter the amount of time we can keep the server components up, the more server components can be created over time, and therefore the higher the throughput. So splitting up the business transaction into smaller transactions joined by message queues actually leads to a configuration which gives higher throughput. We'll look more at this in a moment, but from the client side we end up with fewer downtime due to resource shortages at the server. From the server side we end up with shorter server lifetimes. So let's look at a specific example. Assume we have a system which requires to process 1 million transactions per day. Orders need to be taken on 24/7 basis, and peak loads appear between 9 AM and 12 PM. So 90% of the orders are taken between 9 and 12, a 3-hour period. So that means, on average, we're going to need to process about 300,000 transactions per hour during that period. So the client end, if you like, the piece taking the orders, the capacity needs to be planned to take 300,000 transactions an hour. The shipping component just needs to keep up with the number of transactions per day in this particular example. So say we allow the shipping component to be up 20 hours a day, the other 4 being for backups or some other planned downtime. In order to amortize the cost of the transactions over that period, we only need the ship object to be able to support 50,000 transactions per hour across the 20 hours, and that gets us the same throughput in a 24-hour period. So the machine which is actually processing the shipping requests can be much smaller in capacity relative to the client object. So by controlling the scheduling, you can actually capacity plan the various pieces of the application independently. Well, now that we have actually split the application into multiple pieces, we need to be sure that we get the same reliability characteristics as a single transaction. And using message queuing, we get no loss in reliability. All the queues used to transfer data are transactional, so MSMQ transacted queues are guaranteed to deliver messages exactly once and with no data loss or duplication. So we can guarantee that if we put a message in a queue at the client, it will appear at the server at some point. MSMQ transacted operations can also be undone by transaction abort. So if we have a transaction which includes putting the data in the queue and updating a database, if we fail to update the database, the request won't go into the transacted queue. It will be rolled back. So we can guarantee to keep the database and the queues in sync. And the server can be terminated without data loss because of the transaction guarantees. The server may go down, either planned or unplanned, and when it comes back up, recovery will run, and the queues will contain exactly what they should contain. All the transactions that have committed will still be in the queue, and transactions that aborted will not be in the queue. That covers general message queuing. If we go into queued components now, the principle behind queued components is to allow message-based applications to be developed quickly and easily. So we've seen some of the advantages of message queuing systems, and we want to bring those advantages to applications in a way where application writers don't have to learn new APIs or don't have to learn new subsystems. We want to try and hide some of that stuff from the application developer. So transport details, how the application gets data from the client to the server, should be completely removed from the application. With a traditional message-based system, the application is responsible for marshalling the data that gets passed along the message queuing system. It's responsible for putting the data into the messages and getting the data out of the messages. With queued components, applications use their own interfaces, so it's exactly the same as the DCOM model from that perspective. The application programmer defines components with interfaces, and the clients use those interfaces to interact with the components. And how the messages get from the client components to the server components is completely hidden by the queued components infrastructure. You'll also see that the same binary component, so if we create the shipping component, that shipping component doesn't change whether that component is activated either directly or via queued activation. So the same image, the same DLL, can be activated either as a queued component or as a directly called component, either locally or via DCOM. And QC also provides the infrastructure necessary to write multi-threaded servers. The messages coming over to the server are picked off the queue and can be run in parallel. So QC provides the necessary infrastructure for a multi-threaded server as part of that mechanism. Under the covers, queued components uses MSMQ as a reliable mechanism for moving messages between systems. And like I say, this is all hidden from the application. So if we look at an application written to use queued components, we first start off with a shipping component, and that's defined or written in exactly the same way as you would write any other component. It's a COM plus component which has a number of properties and a number of methods. We then write an order entry system which uses that component as it would any other COM plus component. So we get the object, we access some of the properties, and we call some of the methods in exactly the same way as we would a DCOM component or a local component. The difference with queued components is when you actually create the object, you don't actually create an instance of the shipping object. You create a recorder object. And what the recorder object does is it looks up in the pipe library to figure out which interfaces the shipping component actually implements, and it presents an object which implements the same set of interfaces. So when you call the methods and use the properties of the shipping component, you're actually using the recorder. And what the recorder does is package up any of the requests that you make into a single message. So all the calls in this case to update the properties and to modify the line method are all packaged into one single message. The recorder then uses MSMQ to move that message from the client to the server, or where the shipping object exists. And at the server end, queued components provides a listener. And what the listener does is it picks off the messages from the message queue, and it then passes that message off to a number of players, and there are a number of threads which are created, each of which contains a player. The player is responsible for unpacking the message and actually calling the component, instantiating and calling the component. The recorder is created in the same transaction context as in this case, the order entry object, and the player creates a transaction that runs the shipping object. So going back to this slide with transactions on it, you can see how those transactions map onto the various components. QC tries to provide as much support for as many components as possible, but because of the time independence of the client and server, some thought is required when designing interfaces to run in this environment. So, for example, the client may not be there when the server actually gets to run, or the server may not be there when the client runs. There may be no overlap in lifetimes of the components. So that puts some restrictions on the way in which you can use interfaces. What you really need to do is think of it as a one-way messaging system, where the client sends a message to the server, and the server responds to that message. The server can then send a message back to somewhere else on the client if a response is required, but it won't be back to the same component necessarily as the original request was sent from. The way that's mapped into methods and parameters is basically that you can only provide input parameters to methods. Input parameters have to be by value, and you can't rely on any function return values. So you can't return statuses, you can't return application-specific things via output parameters. All parameters have to be in only, and in Visual Basic that basically means using the by val keyword. You also can't have any application-specific H results. So calling a method may return an H result, but that H result may not be from the almost certainly won't be from the server, because all that happened was a message got put into the queue, and then the method returned back to the client. The server never actually ran in order to get that H result. And the client should expect no synchronous result. In other words, when the client has finished calling the methods on the server, you shouldn't expect that the results that would have happened from that method, those methods having been called, to have actually happened. They may happen sometime in the future. The client can't expect that. Whatever it has to happen has already been done. So that begs the question, how do we actually get output back to the client? I do a request, how do I know what happened to that request? And we can categorize 3 different scenarios where there are various types of why do I want to get output. Initially, we have pessimistic. So it's just like RPC. The client makes a request and expects a response back every single time it does a request. And we'll see how that can be achieved in queued components. There's an optimistic approach, which is I send a request to the server from the client, and I trust that it will happen. I trust that the infrastructure is such that eventually the server will do whatever it's been asked to do, and I don't need to ask for a response in order for that to be the case. There's then a less paranoid case, which is basically to generate selective responses. So, for example, if an exception occurs, maybe I want to see the exceptions, but I don't care if everything succeeded. I just want to see the errors. So there's that class of applications. And we'll see how that can be implemented using queued components. So going back to the request-response type protocol, where I want to get a request, I want to get a response every time I do a request, we can use what QC calls a response object. Essentially what happens is the client, in this case the order component, passes a reference to another component which happens to be sitting on that node, or any other node for that matter, to the shipping object. So in this case, the order component not only passes the order to the shipping object, it also passes a reference to another queued component, the notify object. That actually ends up being passing a recorder over the wire to the shipping object. So the shipping object now has the data it needs to do whatever it needs to do to the shipping, and it also has an object that it can use to notify the client of the outcome. So the shipping object can use that notify object's interfaces in exactly the same way as it would had it been a local object, just as any other queued component. So in this case, the notify object may update the order database with the outcome of the shipping transaction. And that may be a third transaction in this picture. And it can't necessarily give a response back to the original client, because the original client which took the order may well not be there anymore. So we use a separate response object to emulate that. So if we tie that back to the Marge's travel agent, where would we use this particular scenario? What we can consider is a client calls in to make a booking. That booking is put into the order database. So the travel database may be checked. We do whatever necessary checks are there so that the client knows up front whether or not that request can be made. The order is then put into the travel database, and a request is put on the queue to the credit card company or the credit card object to check the credit card details. And that doesn't need to be done initially. Eventually the credit card object will pick up the message, do whatever it needs to do to check the credit card details, and post a message back to the credit card queue as a notify object. That then gets passed back to the client, which may instantiate a status object, which then updates the travel database. So now the travel database contains the status of the order or the travel order that's been made. And so by viewing the travel database, you can see exactly what the status is. So that's kind of ties it back to the travel agency example, and is a good fit for where that might be used in that particular example. So we've talked about normal direct activation using decon. We've talked about queued messages, and we've kind of given an overview of where queued components is interesting or can be used to implement some particular application types. Now what we want to do is go on and look at how you actually use queued components. So initially we have to figure out how to create a queued component. And so what we've actually built is we have two new monikers for component activation. The first one is the new moniker. And what that does is basically accepts either a prog ID or a class ID and allows you to instantiate or activate a component. When it's used on its own, it's just like using co-create instance. It just creates an instance of the object. And you can use any of the existing mechanisms for calling a moniker. Basically use new colon whatever, either the program ID or the class ID. And the examples on the slide show Visual Basic and VC. So that gets us the first moniker, and all that does is create a direct instance. What we actually want to do now is create a queued component. To do that, we use the queue moniker. And the queued moniker composes with the new moniker to create queued components. So in the first Visual Basic example there, we have create a ship object using the queue and the new moniker composed. The new moniker, when composed with the queue moniker, basically returns the class ID of the component to the queue moniker, and the queue moniker then instantiates a recorder checking the type library of that particular class ID and generating a recorder which implements the interfaces defined by that object. The queue moniker can actually carry MSMQ attributes. So if there are specific attributes you want to add over and above the default attributes, that can be done by adding things to the way in which the object is created. So for example here, we're basically saying that the computer name on which we want to instantiate, or the computer name where the queue exists, is actually called Denver, and we want the priority of this to be 3. So you can override the default MSMQ attributes. There are also some QC-specific attributes, like the computer name, which basically affect the destination queue of the object. Explicit attributes are not actually normally required, so the default attributes that you would get by just using the queue and new monikers together is probably all you would need for most circumstances. So what we'll do now is look at a short demo of how to actually implement and deploy an application using queue components. What I want to do is just quickly run through some of the things we didn't cover in the demo, in particular error handling. Sometimes messages can repeatedly abort, so from the client end it may be that the NSMQ can't actually deliver the message from the client to the server. From the server's point of view, it may well be that that particular message containing methods and procedure calls is invalid in some way. So what we have to have is some mechanism where these messages can actually be handled. Normally when a message aborts, it will be put back on the queue. But that means that if a message continually aborts, we end up with a message sitting at the top of the queue which continually aborts and is basically in the way for processing normal messages. So what we have, as you saw in the demo, is a number of retry queues. And as messages abort, they're moved down through the retry queues. And the documentation, which I have a slide at the end to show you where to pick that up, describes the mechanisms by which poison messages are moved throughout the retry queues. Possible options are fix the problems and move the messages back. We have a message mover utility that allows you to pick up messages from retry queues or from the dead queue and move them back into production, if you like. So if you fix a problem with a server, so say the client couldn't connect because of security issues, then you fix the problem to do with security. You can then move the messages back and get those messages to be retried. You may decide to gather diagnostic information and basically just delete the messages from the queues. Or you may generate compensating transactions. So in the case of the travel agency, if the credit card failed and continually fails, you may decide to back out the entire request and send a message back or mail back to the customer that that particular request had been aborted. And it often matches business scenarios. So we can consider how banks handle bad checks. It fits nicely with that model. And by retrying rather than and putting things back on queues rather than retrying by holding on to things, we avoid long lock hold times. So it avoids contention for some of the records. So how do we actually get this error handling to happen? A component installed in a COM+ application has a queuing exception class attribute. And if you look in the component services snap-in for the components, you'll see a tab which is marked advanced, I think, or something like that, which has in there queuing exception class. In there you can specify the name of an exception, the name of an object to execute when an exception occurs. And that object must support the iPlayback control interface. And that has a couple of methods. It has a final client retry method and a final client server. A final server retry method. When messages are moved to the dead queue, so they've been retried as many times as they can be, and we've decided to give up on that message, then the final client retry will be called on the client end, or the final server retry method will be called on the server end, depending on where the retries occur. And that exception class should also support the standard queued interfaces that the object that it is an exception for supports. And what happens then is, before the message is moved, the exception class is called on those interfaces so that you get an opportunity to back out the transaction or generate diagnostic information. So you get to handle the errors as they get moved to the dead queue. That pretty much concludes how to use, deploy, and some of the advantages for queued components. So just finally wanted to finish off with where we were with the project. The NT5 Beta 3 will have a version of queued components, and that will feature basically what was there in the Beta 2, so everything you could do then, plus it'll allow you to pass a queued component interface to another queued component, so it'll allow you to generate the response queues that we looked at in the sample. It also supports non-transactional queues, so if you create a queue outside of the component services snap-in using the message services interface, and you can mark that queue non-transactional, or you can create that queue non-transactional, then QC will actually use that queue. And you can add the MSMQ properties via the queue moniker, so express delivery or whatever you want to add to the messages. Also supported is the queuable interface attribute in IDL, so you can now specify on an interface that it is queuable. And what that will do is, when you load the component into an application, the queuable or the queued checkbox will be checked automatically for you. We also support the setComplete method attribute, so methods can be automatically committed on completion or aborted depending on return status. And we have admin SDK support, so all of the things that you've seen done by hand today in the management interface can be done via scripted or via programs. So what's coming up? There are a couple of things that didn't make it into Beta 3 but will be in the RTM for queued components. The first one is the ability to pass any object subject to interface requirements that supports IPsys stream. So if you write a component which has the interface restrictions that queued components requires, and it supports IPsys stream, then you can pass references to that object directly to other queued components. So in VB you can create persistable objects. What that means is that VB will generate an IPsys stream implementation behind your back for you, and those objects can be passed across to queued components. We also support MSMQ workgroup configurations, so you will be able to create standalone servers with standalone MSMQ workgroup configurations and use queued components on top of that configuration. So you'll be able to develop, test, maybe even deploy applications on single standalone servers without needing primary enterprise controllers or primary site controllers. Queued components doesn't guarantee the ordering of messages. So the QC listener dispatches messages to QC players in parallel. There are no plans in that time frame at present to actually give any way to create an ordering guarantee. Maybe, and we're looking into this, there may be registry options, private registry options which allow you to do that. It's still under investigation.